Hey students, how are you, AP students? Excited for this problem? I'm excited too. Let's give this problem a try. And let's stop this music. Did you like the intro though? The nice soothing little music, you feel nice and relaxed. Let's try this problem. I'm trying to combine a lot of the different techniques that we've learned throughout this chapter. Most of these problems would be found in 6.3, but the last problem we're going to do is kind of an extension of what we learned in 6.3 and then applying it to what we learned in 6.2. And all of this was actually motivated by one of your homework problems, problem number 99. Okay, the average batting average in Major League Baseball is .260. In other words, if a batter comes at bat, there's a 26% chance that they're going to have a hit. A hit is getting on base. Typically, a batter is at bat 4 times in one game. So let's answer a few questions here. What's the probability that he makes 2 hits in a game? What's the probability that the batter will hit more than 1 hit in a game? And by the way, as I'm working through these, I encourage you to pause the video and try it on your own. What's the probability that the batter will make his first hit on the 4th time at bat, or the last time in a game? What's the probability that the batter will have his first miss on the 4th bat at game? The 4th at bat in a game, excuse me. Part 5 of this little problem is how many hits do we expect a batter to make in a game? That was all one part, part A. Part B, a batting average over 30% or .300 is considered really good. If a batter is at bat 500 times in a season, what proportion of batters will hit over 300? And use the 4-step process. We're going to use the 4-step process on this one. This one is pretty much your homework problem number 99. And last part, we're going to get super crazy, and we're going to suppose that the 9 starters for the LA Dodgers had a batting average of 280 over the course of the season altogether. Is this unusual? And let's justify our answer. Ooh, we're getting crazier and crazier, right? All of a sudden these first few problems start sounding fairly easy. Alright, well let's try it out. You ready to start? So again, typically a batter is at bat 4 times in a game. What's the probability he will make 2 hits in one game? In a game, and then again a game is going to be 4 at bats. So you look through this problem and you're looking for 2 hits, and that's exactly 2 hits in a game, which is really 4 at bats. So I see bins, I see a binomial situation. Bins, binary, it's either a hit or a miss. Independent, we're going to assume each bat is at bat is independent in this game. Let's see what else. N, number of trials, is fixed. There's 4 at bats, and we're looking, and the probability of success is going to be .260. So this is going to be a binary binomial distribution. This is going to be, we're looking for the probability that we make 2 out of 4 hits. So this should equal 4 choose 2. Probability of success, .260. This is going to be to the 2nd power, and then the probability of failure here is .74, and that's going to be to the 4 minus 2 power. Or of course, that's maybe a harder way of doing it. The easier way of doing this is going to be binom PDF, and N for P is going to be .26 and 2, and hopefully you can do that in your calculator. I'm going to have to pause and get my calculator. Okay, got my calculator, I'm putting in my values. You probably already beat me to this because you can pause and do this. I guess I could pause too, but it'd be kind of weird if I all of a sudden the numbers came up all quickly, right? I get .222. So there's a 22.2% chance a batter in a game, a random batter, we're assuming with an average of .260 batting average, 22% chance that they're going to make 2 hits in a game. It's not bad. What's the probability that the batter hits more than 1 hit in a game? So this is still binomial. Again, we're assuming 4 at bats. And now we're looking for the probability that somebody's going to hit more than 1. So not including 1, because 1 is not more than 1. So I'm going to have to rewrite this if I want to use my binomial CDF function. This is going to be 1 minus the probability that x is less than or equal to 1, or 1 minus binomial PDF or CDF? Yeah, you got it, CDF, because it's interval here. And 4.26 comma 1. And now I'm going to pause the video and get the answer real quickly. And I got 0.279 after rounds, 27.9. So there's a 27.9% chance that they'll make more than 1 hit. Now, does that seem kind of low? Were you expecting a bigger number? It does seem kind of low, but if you think about it, we just solved the last problem. The probability that they make 2 is a 22% chance. The probability that they make 3 out of 4 is going to be much less, and the probability that they get 4 out of 4 is going to be much less. So it actually seems fairly reasonable to get about a 27% chance to get more than 1 hit. Okay, so part 3, what's the probability that the batter will make his first hit on the 4th time at bat? So we look at this first hit on the 4th time at bat. So this is going to be a geometric distribution because we're looking for his first success on the 4th time. Now a lot of times I look at this and I go, okay, that means he's going to miss, then finally succeed. That's the way I like to look at this. If not, you can use the probability that y equals 4 here, because 4 it's going to be the kth trial, first success on the 4th trial. And you can put this into the formula. This is going to be 1 minus p, which is 0.26, to the k minus 1, which is going to be to the 3rd power, times p. And if I do that, that's going to be 0.74 to the 3rd times 0.26 to the 1st. I get a 0.105, about a 10.5% chance that the batter will make his first hit on the 4th time. Hopefully he'll make one before then, right? I hope so too. Number 4 on this, what's the probability that the batter will have his first miss on the 4th at bat? So the first miss. So we've done a little thing here. We've changed. Before a success was making a hit, now we can think that a success is a miss. And what's the probability of missing? 74%. That's 1 minus 0.26. So again, we're looking here for a fail, and then a success. And again, in this case, a fail actually meant a hit, and then finally the first miss. So this should be 0.26 times 0.26 times 0.26 to the 3rd power times 0.74. And once I do that, plugging and chugging that on my calculator, and I get a whopping 0.013. But that again, what is that implying in this case? That he's actually getting 3 hits in a row and then finally missing one on the 4th chance. So it makes sense that the probability is particularly low. Part 5, how many hits do we expect the batter to make in a game? Again, a game we're saying is 4 at bats. So the number of trials is fixed. So this is going to be the expected value of a binomial situation is going to be NP. So that's going to be 4 times 0.26. Looks like it's just going to be slightly bigger than 1. I didn't do this on the calculator. Let me double check, but I think I'm right. Yeah, nailed it. So we'd expect a batter in any given game to make 1.04 hits, or pretty close to 1 hit. Okay, now we're getting intense, and if you struggled on homework number 99, this is a good problem. In fact, this is pretty much it. Okay, so a batting average of over 300 is considered really good, and we'll consider that over the whole season. If a batter is at bat 500 times in a season, what proportion of batters hit over 300, or .30 if you prefer? Use the four-step process. So, you excited to use the four-step process? Plan, state, do, conclude. No, state, plan, do, conclude. You get out of there. State, plan, do, conclude. So, let's restate the problem. Man, didn't I just write the problem? Tough luck. What proportion of batters hit over .3, that word said over, .300, and I'll say in 500 games, to be just a little more specific, but I could say in a season too, same thing. Okay, plan. So plan. Alright, how are we going to plan this one? Well, if the conditions are met, we will use a normal approximation to a binomial distribution. I'm writing fast, to a binomial distribution. And we're going to have to get a little tricky here, but we're going to let x equal the number of hits in a season. Okay, that was the plan part. Oh, do you want me to go back? Oh, no, wait, there I am. Now I'm back. We're going to let x equal the number of hits in a season. Okay, now we got to do the doing part. I want to use a normal approximation. I planned on using a normal approximation. So I'm going to use a normal approximation. And as I said, if the conditions are met, now I can do this. So the conditions here, the conditions are that NP has to be greater than 10 and N1 minus P has to be greater than 10. Well, what is N? N is going to be 500. That's the 500 at-bats. And we already know P is 0.26. So NP is going to equal 500 times 0.26, which is 130. And last time I checked, 130 was greater than 10. Check. I know you guys like my Christmas colors I'm using. How about N1 minus P? That's going to be 500. 1 minus P was 74, probability of missing. And 500 times 0.74 is going to be 370, which very clearly is greater than 10. And check. So the conditions are met. Now we can so that what is that going to mean? That is going to mean that x follows a normal distribution, and the expected value we've already or the mean of x we've already calculated is NP, and we calculated that above. That's going to be 130. In other words, in a whole season, out of 500 bats, we'd expect the average batter to have 130 hits. Standard deviation is going to equal the square root of NP1 minus P, and N was 500, P was 0.26, 1 minus P 0.74. I'm going to pause and plug those numbers into my calculator. Standard deviation 9.81. So we know now, what have we done here? We've found that x follows a normal distribution. Average batters, we'd expect to have 130 hits out of, and the standard deviation, is 0.801. So trick here. What are we trying to find? What are we trying to find? Well, we wanted to know if a batter hits 300 or more. Well, if the batter is hitting 500 times, how many hits does he have to hit to make 30%? Well, that's going to be 500 times 0.3. So we're really looking for the probability that that a batter hits over 150 hits in a season. And so we are looking for, here's their bell curve. We have an expected value of 130, and we're looking for the probability that a batter hits 150 or more. And we have everything we need here, so we're looking for the probability that x is greater than or equal to 150, and that's going to equal, if I take a z-score, 150 minus 130 over 9.81, that was our standard deviation, and that's going to equal 20 divided by 9.81, which is 2.03. That's going to be the probability that z is going to be greater than 2.04 if I round it. And I'm going to normal CDF this. I already got my z-score, so when I don't need to write this step in my work, but I'm going to write it for you so you know what I'm doing. I'm looking for, well, let me just draw here. If this is x, 130 and 150, then z, here's 0, and this 150 corresponds to a z-score of 2.04. So what I'm going to do is I'm going to do normal CDF 2.04 and off to infinity 99999, and I don't need to put a mean in the standard deviation because it without one it assumes the number I'm putting in is a z-score. So let's do that, and I get 0.0207. Am I done? No, I'm using the four-step process. I got to conclude. I did all that work. Now I need to write a good sentence concluding. There is, or it asks what proportion of remember we're we're answering our question in the state part. So what proportion of batters bat over 300 in a game? We would say that the proportion of batters who hit over 500, over 300, or 0.300, is 0.0207. Nailed it. Yeah, so that was the four-step process. Okay, here's the really fun problem here. Suppose that the 9 starters of the LA Dodger had a batting average of 280 over the course of this season at 500 at-bats. Is this unusual? And justify your answer. So all 9 batters together had an average of 280, and we knew the typical batting average was 260. You ready for this one? So I'm not going to use the four-step process, even though we could. But like before, I'm going to let x equal, in this case, this is going to be the number of hits in a season. Now I'm going to have to do a transformation. I'm going to have the total that, since I'm looking for all 9 starters, that all of them together is going to be x1 and x2, and we're going to go all the way up to 9 different batters, so up to x9. Yikes, this looks hard, right? No? Easy cheesy? Well, what is the mean of x? We've kind of already learned, or we did this before, that the mean of x is 130. That is, if they bat 260, we'd expect an average batter to have 130 out of 500 hits. Okay, well, we found the standard deviation of this distribution too, did we not? 9.81. We did that hard work already. So now we have to look at how many at-bats, how many hits we have. So what we're going to do here, let's find the standard deviation now of t. Let's do this here. So standard deviation of t, well, this is going to be the standard deviation of x1 plus the standard deviation of x2 dot all the way out to the standard deviation of x9. Well, all the standard deviations are the same, 9.81 plus 9.81 plus dot 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 all the way out here to plus 9.81, excuse me. How many of those were there? There were 9 of those, so 9 times 0.81. So that's going to be like the square root of 9 times the square root of 0.981. And that's going to equal 3 times the square root of 0.981. And when I do that in my calculator, oh, hey guys, did I forget something? I knew I forgot something. Something was weird. Oh, Mr. Bessling, minus points. You can't do that. Minus points. All these are squared, right? Mm-hmm. Yep. And that means, there we go. You guys catching my mistake? Hey, I'm human. At least I catch my mistakes. And at least I admit my mistakes. Admit your mistakes first, and then go back and catch your mistakes in the future. So this distribution has a standard deviation of 29.83. And I didn't get into the expected value. I should have done that first. Or the mean of t is going to be the mean of x1 plus the mean of x2 plus dot 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 all the way to the mean of x9. And again, we expected 130. How many 130s? 9 of them. So that's going to, I'll write that over here, equals 9 times 130. And the last time I checked, 9 times 130 was 1,170. And the last time I checked was like 10 seconds ago when I put it in my calculator. Okay, so let's figure out what we have here and what we still need to solve. We have the mean and we have the standard deviation. Now, what does this mean down there mean? What does that expected value of t mean? That would represent, out of all these 9 starters, how many hits combined we would expect them to hit over the season. And this would be of any team. So this would be, you could think of all baseball teams here. We'd expect on average that they hit 1170 for all 9 players. That's 9 times 130. And we had a standard deviation of, I forgot already, sorry, 29.43. But let's remember the Dodgers said that they hit 280 for the season. Well, that's 280 times the 500 at-bats times the 9 different batters. And that's going to equal 1260. In other words, if by the Dodgers hitting 280 in the season, that means that they had to make 1,260 hits. So what are we looking for here? We're looking for the probability t is greater than or equal to 260. Is this extreme? Extreme. It looks pretty extreme to me. Let's find out. We'll just leave that there. 260. So let's take a z-score. That's the probability that z is less than greater than or equal to 1260 minus 1170 divided by 29.43, which looks like it's going to be a z-score just a little over 3, which is going to be fairly extreme because I have 1260 minus. I know that's 90. I don't know why I'm putting it in my calculator anyway. 29 divided by 43. I'm getting this z-score. This is like the probability that z is greater than 0.36, which let's normal CDF this. That's going to be normal CDF normal CDF 3.06, and infinity, and I get 0.0011. So, boy, that was a lot of calculations. I must be done, right? No, Mr. Bessling, you're not done. You're not done. Why am I not done? Because I didn't answer my question. And the question was, is this unusual? And what makes this unusual? Well, unusual is that that if we expect all this to be true, then the odds of a team or 9 players together batting over 280 or essentially getting 1,260 hits in a season is a 0.11% chance. That's pretty low. So I'm going to go ahead and make my conclusion. Since the probability of 9 players, I should kind of say 9 random players because we're assuming they're random players. The probability of 9 random players hitting over 280 in a season is, I'll write it as percents here, 0.11%. We feel we can conclude that this is unusual. Can conclude. Right, something's usually unusual if it only occurs 0.11% of the time, right? We can include that this is unusual. All right, how'd you feel about that last problem? That was kind of tricky, right? That was pretty tricky. Well, I hope you understood it. Are you going to need to know something that hard for your test? Yeah, maybe, maybe not, probably not. But I could see a problem like this being on the AP test in the sense that it's difficult and involves some critical thinking, and as you can see, the questions are really open-ended. The questions are open-ended, but they require specific solutions and justification. I can't just say, yeah, it seems really unusual. No, it doesn't ask me for a calculation, this problem. But I need to do a calculation. I need to calculate to answer the fact that this is unusual. Well, I need to find the probability of it occurring by random chance, and that's pretty low. So, what could explain this? Well, the Dodgers have a lot of money, and they maybe got some really good players, and that's why they hit so phenomenally in this particular season. All right, happy studying. I hope that problem helped. I'm going to slide here. I'll start from the beginning, and I'm just going to slide screen by screen in case you want to pause anything and take any notes. So screen 1, 2. Should I play some exit music? My computer fell asleep. Or did it? All right, guys. Good night. Thank you.